Well, thank you for giving me the opportunity and give the first talk of these sessions. It looks like a very exciting sessions. And what I'm going to talk about really integrate approach and to understand the Earth core. And I have a great teams and who specialize in various area, include geochemistry and mineral physics, of course, and the different aspects of mineral physics measurement include transport property measurement, very ultra high pressure, and as well as shock wave compressions. So what I want to do is, in order to understand the core, is really go back and the planetary formations and through collisions, and really this in the end, and now trying to convince you they're all connected. We really need a kind of taking the integral approach and to understand the final compositions and match of the observations. And so certainly it's very important in this differentiation, interior differentiation process, and start from the low pressure metal percolations to the core mantle differentiations to ultimately the inner core crystallizations. All those relate to the thermal evolutions as well as element redistributions and through metal silicate and separations as well as the inner core growth. So really the fundamental observation we need to match is observe the density and velocity profile as well as the liquid outer core and solid inner core, and as a result is the convection of the liquid outer core and yields the magnetic field. And all those are the final product that we really need to match up and to understand them. But how we do this? And as the experimentalists, we have a static compression as well as a dynamic compression, be able to access different PT regions, and importantly, there's different accuracy of the different data, and as well as the different state, and solid state and liquid. And for the dynamic compression, we can do much better on measuring the density of the liquid and the sound velocity, Bach sound velocity, for example. So it's really important to integrate those, and because we have the solid inner core and liquid outer core, we need both information on the solid state and liquid state, as well as the complication of the composition. I'll come in a little bit later and trying to address those too. So my groups have been working steadily on the static compression data, mostly on solid through X-ray diffraction. I also have collaboration with Daniel. There will be a talk, I think, later on the in-last scattering and aspect. And more importantly, I also kind of started collaborations with a Chinese group and doing shock compressions and be able to access the liquid state as well as sound velocity measurement and for using shock compression techniques. So those are some of the aspects that we need, but obviously there's lots of groups and doing very similar things, but it's important that there's a group have, a different group as come to some data sets, and ultimately we can integrate to build a PVT as a function of compositions and as well velocities. So that's really the ultimate goal. And so really, last AGU I talked about example of the HCP ion, and this is one of the fundamental property of the density, and because we need a reference model, and so far all the published data include the data we recently produced, and produce a very nice data set at room temperature. This is based on various different pressure scales and self-consistency, and it's a remarkable agreement, all those different experiments done by different groups, and as well as different pressure standards. The deviation of this new equation state is within 2%. And except the early data, which has understandably is a larger X-ray spots, but everything done after 2000 is really within the 2%. This is as good as the pressure calibration scales, and we also done some silicon composition. So this is one aspect. You can look at the composition effect and all those experiments done. But what important is also to bring in the dynamic data and really look at the thermal equation state. And of course, for the static compression, we're also getting high PT data, but it's a limited temperature range. And actually, it's very important to extend the static data combines the dynamic data and in different directions. So we really have a thermal equation state and over very large PT range. And so this is all can be modeled. We have a very good thermal equation state. And I think I'm jumping a bit fast, partly because I really want to get to the composition part. And so based on the new silicon content, we can have an inner core, for example, and 5% silicon. That's the up limit to match up the density, for example. And for the static dynamic compression data, we look at the iron sulfur system, have 10 weight % sulfur will match the liquid. So based on the mineral physics data and those measurements, you really can produce a set of composition, be able to match those observations individually in terms of inner core and outer core. Depends how you define the composition space and how well you define the PVT data and the velocity data. And this is only I'm talking about the density data, and the other aspects we're doing is the velocity data. So because of the time limit, I really want to just focus on the density part. So really, the key aspect is not only match up the density and velocity of the liquid outer core and solid inner core, whereas arbitrary composition be able to produce the matched profile. And what we really need to look at this density and the velocity jump. So for example, if you have an inner core composition and the liquid outer core compositions, how you're going to link these two together. So that's really bring me the main talk of this presentations. I want to talk about the element petition and ultimately at the inner core boundary pressure. So that's really the key parameter which we will be able to tie up all the mineral physics data and combine the geophysics, the chemistry data, and to build a much more robust and composition model for inner core and liquid outer core. So we have been doing this element petition, for example, sulfur and iron systems, and in the multi-envelope, and we can map up the phase diagram very nicely and look at the solid and liquid part and measuring composition, really define the phase diagram. So in general, because we know the density deficit in the inner core is smaller than liquid outer core, so we know a system has to be similar to solid core, has less dissolved light element, and liquid has a high percentage of the light element, so produce this density jump. And this is all systematic you can do, but the limitation is really you only can do to about 25 GPa. Actually, with the center diamonds in the multi-envelope, you can push a much higher pressure. And one of the recent things we have also looked at is the silicon effect, because silicon is actually very interesting elements. And if you look at what I presented earlier was silicon content in the inner core limits to 4%, 5%, for example, and really well defines how the silicon is going to partition in a liquid systems, and they're going to put as an upper limit how much silicon you put it in. So ideally, you can produce a detailed phase diagram like this, really look at the composition of the inner core, outer core based on this partition basically in a multi-component systems. In this particular set of experiments, we look at the silicon effect on the sulfur partitions and doesn't affect that much, but the important part is the iron silicon alloy is the liquid phase, and which is precipitate, and much of the initial silicons goes to the solid inner core, and equivalent to if you can produce a phase diagram like this at 330 GPa. So that's really the key, how we extend this to the inner core boundaries. And we need to really, be able to produce data and similar into the multi-envelope, convince ourselves, have good phase equivalent data. And so that's pretty much the last few years, my efforts is trying to really extend this using laser heating diamond cell. This is the only technique and be able to produce that kind of inner core conditions, be able to recover example. So the approach we're taking is laser heating sample and define the sample, and then using FIP technology and to recovering sample, then doing composition determinations. So that itself sounds straightforward, but the challenging is really the small sample and equilibrium, how you define these homogeneous compositions. So one of the things we have been working on is really have a new concept of sample chamber and EMO design, be able to get to higher pressure, be able to recover in sample. And again, remember, when you do diffraction, you can bring up the bin synchrotron and do as high as the pressure you want to do and break the diamond. But this type of experiment, you really have to think ahead, and you want to recover the sample. You want to push the limit, but still be able to recover in sample. So sample design is very important, and I think we have kind of figured out some way to really try and understand how to do the melding experiment, particularly isolate the sample from the surrounding, which is almost like a small capsule, because invariably when you start to have a partial melding migrates, and that's going to affect what you're going to measure on the petition. So it's very important to isolate it. We're using this two-stage envelope. We can consistently get to 200 GPa recovering sample. I have a set of envelope, has done 3 experiments and still be able to reuse it, and over 150 GPa and no ring crack. So this is a really significant development, and also using FIP fabrications to redesign the envelope, redistribute the stress, and no ring crack and after recovering. So those are very important aspects. I want to just show you a few examples, and at relatively low pressure, because right now the easiest experiment to do is under 100 GPa with a single stage envelopes, and those we can do multiple experiments. We really need to understand the system, how to do those experiments, convince ourselves, and those are reliable and reproducible data, and really showing. So this is one example. You can see we isolate the sample, laser heating to different temperature, be able to individually look at each of those samples. This is one of the recovered samples, and if you look at it, it's basically look at the ion and the oxygen map. And now we can do oxygen partitions between ion and the melts. And so really the next step is be able to do quantitative measurement. And we're very excited that we're actually going to have a new field emission electron microprobe installed in February at the geophysics lab. Right now we can do those quantitative measurements with the silicon derivative detector. So we are still in the stage of derivative techniques, and I'm going to show you some beautiful map, and not showing the actual data yet, because I hate going to revise those data and after a couple of months and redo those analysis in wavelength spectrometers. But in any case, and we can do this kind of petition experiment very nicely, and this is another example. And again, and with this sample design techniques, we can confine the melding. We really look at the coexisting of the solid and liquid phase and be able to do the phase diagram. And ultimately, we want to take this type of a protocol and measurement goes beyond to very high pressure. And obviously, those are much more costly and challenging. And we have a few quantitative examples. One of the highest pressure we quantitate the melding is at 330 GPa, and we'll be able to do mapping and look at the individual composition and melding textures. And another example is we have done those experiments at 278 GPa. Definitely they're molten, and we'll be able to recover in the sample and look at a mapping of there. So again, look at the scale bar. This is 2 microns. So we really need a sub-micron chemical analysis. So ideally, you need to be able to get down 250 nanometers. So we're doing lots of technical development, doing sub-micron and down to 200 nanometer and chemical analysis. And this is really exciting, next few months and years, and we are really going to produce lots of those data and look at detailed recovery sample, textures and equilibrium, and at different PT conditions, and ideally be able to generate binary and multi-component system phase diagram and different pressure ultimately to 330 GPa. So really, I want to summarize is the static dynamic experiment provide the complementary data to model the core properties, and also include the very accurate density measurement up to 200 GPa, and some velocity measurements, and right now, mostly at the room temperature, low temperature, but for the PVT question state data, we can go to much higher PT conditions, and then ultimately really doing the petition and further constrain the composition of the core. And right now we're at the stage we can recover routinely at 100 GPa, and with some efforts, 200 GPa really break lots of diamonds, and when you go to 300 GPa. But that's something, the price we have to pay. Thank you.
Okay, we have time for one quick question. In the back.
Yeah, in those systems, we really have no way to control them, but really trying to control the initial composition, assume if you have a closed resistance. And that's actually very good questions. We actually recovering all those iron melting sample, we have not seen a pure iron melting. It always contains some oxygen. So the question is the oxygen may be, if you load the grain, I'm pretty sure there's oxidized fumes on the grains, and which could be in the loading process incorporate the oxygen. So that's one of the example I showed. The oxygen petitions, actually that experiment was designed for pure and iron, and we are seeing and quite a substantial oxygen. We can do actually the oxygen petitions. Yeah, that's a very good. I think in the future we really need. I always say you can't really do careful experiment if you don't have the environment. You can't do clean an example if you not have a clean rooms, right? So really we have to think about that too.